Okay, just part A, and then I'll give you a little more time. The answer to part A is like those reality shows where they don't tell you who's been voted off before next week. So you gotta have that pause for dramatic effect. Plus Y. And here's how I got it. We have a magnetic field that points away from you. So that's what the X's mean. Dots are arrows that stick out of the page toward you. X's, you're looking at the back end of the arrow. We have a charged particle. Yeah. If some of you are sitting out there with negative Y, you may have overlooked the little minus sign drawn on the particle. This is an electron or a negative ion or something like that. With a negative charge, with Q being a negative number, the force in V cross B have opposite directions. But got a minus charge, and its velocity vector is this way. And so it helps. You can make a little model out of pens and pencils. The red one there, that's for the camera. That's the negative Z direction for the magnetic field, and pencil is the velocity vector, and so the force has to be perpendicular to both of these things. Once again, the right-hand rule is just for choosing between two alternatives. Before you do anything with your right hand, you should be able to see that the answer is either plus Y or minus Y, because the force has to be perpendicular to both of these vectors. So you get your right hand and you wrap your fingers around the Y-axis, pointing from V toward B, from the first vector in the formula to the second one. So V cross B points downward. But once again, because it's a negative number for Q, Q times V cross B points the other way. It's the positive Y direction. The thing down in the bottom right-hand corner there says the plane of the page is the XY plane. Not all textbooks are written that way, so I figured I'd better include that. Anyhow, we'll pause here for a few moments. Where did I go? Still see a few people out there accidentally saying things they didn't mean in sign language, but I think most people have done as much of this as they're going to. So part B, hopefully you realize that there is no force on the charged particle in this case. It shows in the picture that the direction of the magnetic field is upward. It shows that the direction of the velocity vector is downward. So when I first started talking about magnetism the other day, maybe you remember me saying that the force is a maximum when the particle cuts across the field lines. If it's going along the field lines, there is no force. Where that shows up in the formula is in the sine theta factor. If V and B have opposite directions like this, when you stick the arrows together, they make a 180-degree angle. Sine of 180 degrees is 0. And so there's nothing to do with your right hand in this one. There isn't any force to find the direction of. Part C, the direction is negative y. The thing's coming out of the page toward you. So the dot this time is the velocity vector. And the magnetic field vector points this way. So you do the right-hand rule thing. V cross B would point up the y-axis. But kind of like in the first one, it's a negative particle. So because Q is a negative number, Q times V cross B has the opposite direction that V cross B does. So as I said, the answer is negative y. Part D, the answer is negative x. So this time it's the magnetic field that's pointing out of the page toward you. Particle is headed toward the bottom of the page. So if that's V and if that's B, then let's see. Wrap your fingers around the origin pointing from V toward B. Looks like my thumb points to the left. Completely, there it is. And this time it's a positive particle, so that doesn't reverse the direction. Q times V cross B has the same direction that V cross B does, Q being positive. And then the last one, hopefully this one was fairly obvious. Somebody tell me the last part. None, because of the V factor this time. If it's not moving, there's no force. B equals 0, Q times V cross B is 0. Okay, next page. I already did the part about the circular motion of a charged particle in a magnetic field. Maybe one application, I talked about mass spectrometers and things like that, but if you want to get into just pure physics research, this is how they identify the charge and the mass of particles produced in particle accelerators, where they smash particles into each other and look at what comes flying out and try and probe the basic structure of matter that way. They always have a magnetic field in the area around the collision site. And if you look at the paths followed by the particles that are produced, first of all, which way they curve tells you if they're positive or negative. A positive part, having different signs on Q reverses the force would be in one direction for a positive particle and other direction for a negative particle. So If it curves the one way, it's positive. If it curves the other way, it's negative. If it just goes straight, it's neutral. And the radius of curvature, and that part's already all in your notes. It should say there from the other day that R is equal to mv over qb. But the radius of curvature tells you or it's one of the factors at least that tells you the mass of the particle. All else being equal, a lightweight particle would curve very sharply. A heavier one would have a more gradual curve to its path. Anyhow, QVB equals mv squared over r. That's what that was. The Lorentz force equation. Well, I've talked about particles moving through magnetic fields. Earlier in the course, I talked about charged particles in electric fields. What if both kinds of fields are present at the same time? Well, this doesn't actually take very long to come up with a formula. You just add the two things together. Particle in an electric field from the first week of the course. An electric field creates a force equal to Q times E. From more recently, if a particle is in a magnetic field, feels a force equal to Q times B cross B. If both are present at the same time, it's just the superposition principle. Add them together. And that's all Lorentz had to do to get an equation named after him. Well, I guess a lot of it is being in the right place at the right time. Somebody needed to put together a general equation for the electromagnetic force from which both of these things follow as special cases. And that person who happened to be in the right place at the right time was Lorentz, I guess. Oh, I'll get through this example in 4 minutes. Probably not. I've gone over a few times on you, so I probably owe you the 4 minutes. And I should even things out. So if I go over again by a couple minutes next time, you can't say much. Oh, one thing I wanted to mention before I let you go. This is a just in case kind of thing, but it crossed my mind. There's been all this fuss in the news about the coronavirus, and I haven't heard anything from the administration on this yet. But the last time that there was a lot of hype about a disease was when we had the H1N1 flu strain a few years ago. Maybe you remember that. And
It almost killed me.
what?
It almost killed me.
Oh,
It was
well, the
not
almost
like
part is
ice.
good.
Yeah.
Well, anyhow, we were, at that time, we got told by the powers that be that we should be sure our students understood what to do if for some reason they decided to close the college to keep people from infecting each other. So that you didn't all almost die like she did. But I'm just going to say, because we're coming up on spring break, and if things rapidly evolve when you aren't here, I figured I should say something now. Just one possibility, and this never happened with the other virus, and it's almost certainly not going to happen this time either. But one possibility is if we all get told that we have to stay in our bedrooms for a week and not come out, I could start recording lectures from home. So I will post instructions at least in Blackboard. I don't know if I can get to the other website from my computer at home to do anything to that, the one with most of my stuff on it. But I'll put some kind of instructions in Blackboard as to what, how we'll keep the course going if that was to happen. And that might mean that you still have to go to your physics class Monday and Wednesday and Friday at this time, but that you have to watch it on your phone or something like that until we get the all clear. And then we'll have a whole bunch of labs to make up. I'm not quite sure how we'll do. I might have to cancel some of the labs. I don't know.
Well, I mean, if we are all watching the recordings at home, that means that all of our class time can be dedicated to the relay.
You stop giving me ideas.